A single invisible thread connects the pyramids to the skyscrapers. It is not just an idea, but a physical revolution hidden in plain sight, the story of how composite construction techniques completely reshaped our world. By the end of our journey, you will see every monumental building in history through an entirely new lens, understanding the secret alchemy that made it possible. How did a simple mix of mud and straw lead to the domes of Rome, and what forgotten recipe allowed ancient concrete to outlast our own? This is the silent partnership of materials that allowed human ambition to literally reach for the sky. What do you believe is the ultimate limit of what we can build? This architectural alchemy has a name, and it is far more precise than we might think. To grasp the true scale of the revolution, we need to define it clearly. Composite construction is not just about using two different things in the same building. That is merely assembly. True composite technique is about synergy, the intelligent partnership where each material does what it does best, covering for the weaknesses of the other to create something entirely new and far stronger. It is a conversation between substances, a physical dialogue that answers a problem no single material could solve alone. Consider the inherent limits of our oldest building blocks. Stone is incredibly strong when you push down on it, what engineers call compression. But try to bend it or pull it apart and it will snap. It has poor tensile strength. Wood, on the other hand, is flexible and resists pulling forces well, but it can buckle under heavy, constant weight and is vulnerable to fire and decay. For builders were confined to these natural limits. A stone lintel over a doorway could only span a short distance before it risked cracking under its own weight. A wooden roof could only cover a modest space. The architectural world was a series of closed doors, until someone asked a brilliant question. What if we stopped asking one material to do everything and instead let them work as a team? This is the core idea. It is the moment we moved from monolithic thinking, relying on one homogeneous substance, to a composite mindset. This shift is not just technical, it is philosophical. It is the recognition that strength lies in strategic combination, in unity through diversity. And this simple, powerful idea born from necessity is the silent key that would eventually unlock the dome of the Pantheon, the Gothic cathedral, and the steel-framed tower. It all starts with that first, ingenious partnership. That first partnership was forged from earth and sunlight. The earliest builders did not have stone quarries or metal forges. They had the ground beneath their feet and the plants growing around them. Their challenge was simple yet profound: how to turn soft, shapeless mud into a solid, reliable building block. When wet clay dries, it shrinks and pulls apart, creating a network of cracks that weaken the entire structure. It is a brittle material, destined to fail on its own. But somewhere in a moment of forgotten genius, someone mixed chopped straw into the mud. This was not decoration, it was a revolution. The long, fibrous strands of straw acted like a primitive reinforcement net, holding the clay together as it contracted. The straw provided tensile strength, resisting those internal pulling forces, while the clay provided the bulk and compressive strength. Together, they created adobe, the world's first engineered composite material. This was more than a new recipe, it was a new way of thinking about materials. It recognized that weakness could be designed out through combination. With these sturdy, uniform bricks, architecture could truly begin. Walls could be built higher and rooms could be planned and structures could last beyond a single season. We see this legacy in places like one of humanity's earliest known cities, where homes were built entirely of mud brick, sharing walls in a dense, interconnected hive. This was the leap from temporary shelter to permanent community, all made possible by straw and mud. That humble mix is the direct ancestor of every reinforced concrete skyscraper today, the same principle scaled up over. It proves that monumental architecture does not start with grandeur. It starts with solving a basic problem in an ingenious way. From mud and straw, the next leap required fire and earth on a monumental scale. The Romans looked at a landscape shaped by volcanoes and saw not just destruction but potential. They discovered that the very ash which buried towns, a fine powder called pozzolana, held a secret. When mixed with lime and water, it triggered a chemical reaction that produced a binder of astonishing strength. This was the heart of opus Roman concrete, a composite that would build an empire. The genius was in the combination. The lime and pozzolana paste acted as the perfect glue, while the aggregate, often rubble from older buildings or local stone, provided the bulk and compressive strength. But the real magic was in the curing. Unlike modern concrete, which simply dries, Roman concrete underwent a slow, hot chemical process that created incredibly stable crystalline structures. This meant it could harden even underwater, growing stronger with time as seawater percolated through it, actually healing tiny cracks. This single property changed everything. It liberated architecture from the ground. No longer were builders confined to dragging massive stone blocks into place, limited by the tensile weakness of lintels. Now, they could pour fluid stone into wooden molds, shaping space itself. They could create curves, vaults, and domes of a scale previously unimaginable. The ultimate testament to this power is the Pantheon in Rome. Its dome, a perfect hemisphere of concrete, spans 142 feet and remains the world's largest concrete dome nearly 2,000 years later. Stand inside and look up, and you are not just seeing a roof, you are witnessing the triumph of a composite idea. The dome is not a solid, homogeneous mass. It is a carefully engineered gradient. At its thick, heavy base, the concrete is mixed with dense travertine stone. But as the dome curves upward, the builders lighten the mix, using progressively lighter aggregates like pumice at the very top. They understood load and stress intuitively, tailoring their composite material throughout the structure. This is not just building, this is a symphony of material science. With this technology, Roman ambition took physical form. Aqueducts marched across valleys on slender arches of concrete, bringing water to cities. Vast public baths with complex vaulted ceilings became social hubs. The concrete revolution enabled an architectural language of immense interior space, of light pouring through oculi, of curves that directed the eye and the spirit upward. It was a style designed to inspire awe, to make the individual feel both dwarfed and elevated within the empire's embrace. This was not merely an improvement in technique, it was a redefinition of what architecture could be and what it could represent. The empire was built not just by legions, but by this quiet alchemy of lime, ash, and water. But the fall of Rome did not end the story of composite construction, it merely sent it into the rafters. Within the soaring stone shells of medieval cathedrals and great halls, a new kind of skeleton was being forged in secrecy, high above the heads of and nobles. The walls were still made of massive stone, defining the sacred space below, but the roofs that sheltered these vast interiors faced a different challenge entirely. Spanning a wide nave with heavy timber was a battle against gravity itself. Wood is strong but flexible, and over a great distance, the weight of the roof itself creates powerful outward thrust, a force that pushes the walls apart. A simple wooden beam would sag, and the entire structure could collapse. The medieval master carpenter, working alongside the blacksmith, found an ingenious composite solution. They developed intricate timber trusses, complex frameworks of beams arranged in triangles, the geometric shape of inherent stability. But the true innovation was hidden at the joints. Here, the blacksmith's art came into play. They would forge heavy iron straps, long iron rods known as tie beams, and sturdy braces. These were not mere decorations, they were the architectural tendons of the building. The iron was hammered hot around the wooden joints, binding them together with incredible strength. When the heavy timber frame tried to flex or pull apart under the roof's load, the ironwork absorbed those tensile forces, the pulling stresses that wood handles poorly. This iron and timber partnership created a hidden composite skeleton, a flexible yet immensely strong lattice locked in a constant, silent dialogue with gravity. This hidden system allowed for miracles of interior space. It led directly to the development of the hammer beam roof, a masterpiece of medieval engineering seen in places like Westminster Hall in London. This design uses short horizontal beams, the hammer beams projecting from the walls, supported by curved braces and tied together with iron. The effect is a roof that seems to float, creating a cavernous, unobstructed volume below that feels both sheltered and expansive. The grandeur of those medieval interiors, the sense of awe as you look up into that intricate wooden vault, was not just an artistic achievement. It was the direct result of a composite system, a calculated partnership between the organic strength of timber and the forged resilience of iron, working in unison to defy the very forces that sought to pull them down. This was architecture learning to fly, not with wings, but with geometry and cold iron. Stone learned to fly on the tips of 1,000 arches. The Gothic cathedral is not just a building, It is a diagram of forces made visible, a structural symphony composed entirely in stone. At its heart are two revolutionary inventions, the pointed arch and the ribbed vault, which together represent the ultimate expression of composite thinking in a single material. They solved the fundamental weakness of their Roman predecessors. The classic rounded arch creates a powerful outward thrust, pushing against the walls that contain it. To counter this, Romanesque churches needed massive, thick walls with few windows, creating dark, fortress-like interiors. The Gothic master builder saw this not as a limitation of stone, but as a flaw in the geometry. The pointed arch is a stroke of genius. By steepening the curve, it directs the weight of the ceiling more directly downward, reducing that sideways thrust. It is a more efficient shape, channeling gravity's force with elegant precision. But this was only half the equation. The true magic happens overhead in the ceiling. Here, the ribbed vault turns the entire roof into a composite system. Think of it as a permanent stone skeleton. Master craftsmen would first erect a framework of slender, interlocking stone ribs, arching gracefully from column to column. These ribs were the primary structure, the load-bearing bones of the ceiling. Once this stone skeleton was locked in place, the spaces between the ribs, called the webbing, could be filled. This infill did not need to be massive, dense stone. It could be thinner panels or even lighter brick. The ribs carried the load, allowing everything else to become lighter. This was distributive composite construction in its form. The ribs gathered the weight of the entire roof and funneled it down along precise, predetermined paths to the clusters of columns below. This simple but profound redistribution of force changed everything about what a wall could be. Since the walls between the columns were no longer holding up the roof, they were freed from their load-bearing duty. They could be dissolved, replaced by vast, towering windows. Stone masonry transformed into stone lacework, and that lacework became a frame for stained glass, transforming sunlight into a divine narrative of color and light. The entire architectural goal shifted from creating solid, imposing mass to achieving an ethereal, vertical aspiration. Walking into a cathedral like Chartres or Dame, you are not standing under a ceiling, you are standing inside a three-dimensional stone diagram. Every rib, every column, every flying buttress outside is part of a single, integrated system, a composite organism in stone designed to defy weight and embrace luminosity. The Gothic style was not an aesthetic choice that then found a structure. It was a structural revolution that created a new aesthetic, one where engineering and spirituality became indistinguishable. The secret to reaching heaven was not just faith but geometry, yet that soaring stone skeleton could not answer every architectural dream. The Renaissance looked back to Rome with profound admiration, yearning to recreate its marble-clad grandeur, its sense of perfect proportion and imperial calm. But there was a problem, one of pure economics and physics. Building a new Peter's Basilica entirely from solid marble blocks, as the ancients might have done, would have been astronomically expensive and impossibly slow. The architects and patrons of the era faced a creative dilemma: how to achieve the scale and splendor of antiquity with the practical realities of their own time. Their ingenious solution was a kind of architectural deception, a brilliant composite strategy that separated the bones of a building from its skin. The method was known as brick core construction with stone. In essence, they would build the vast structural form of a palace or cathedral not from expensive stone, but from a fast, economical core of brick or even rubble concrete. This core provided the strength and the shape, erected with remarkable speed by teams of masons. Once this robust skeleton was complete, the true artistry began. Craftsmen would then clad or veneer this brick core with a thin, elegant skin of finely cut travertine or marble. This outer layer, though, was purely aesthetic, a magnificent facade that presented the illusion of a solid stone monument. Think of it like a beautifully bound book, where the covers are exquisite leather, but the pages inside are sturdy, practical paper. This composite approach was of efficiency and artistry. It allowed a figure like Michelangelo to design the monumental dome of Peter's, a structure of breathtaking scale, without requiring a mountain of solid marble. The dome's inner structure, its ribs and shell, were built of brick, a material that could be easily shaped into complex curves. Only later was it planned to receive its outer skin of stone. This division of labor between structure and surface liberated architecture. It meant the structural engineers could focus on stability and form, while the artists and sculptors could focus on proportion, detail, and symbolic decoration. The classical orders, the columns, pediments, and intricate friezes that defined the Renaissance style were no longer load-bearing necessities. They became applied elements, a visual language of power and learning that could be attached to the building's face. This is why Renaissance palaces in Florence present such imposing, perfectly ordered street fronts, while their inner courtyards and side walls often reveal the humble, practical brick of their true construction. The style was a grand performance, a testament to the humanist belief in ideal forms, made possible by a very pragmatic composite reality. The splendor was not a lie, but a collaboration, where the strength of brick married the beauty of marble to resurrect the spirit of Rome. Hidden within the soot-stained brick walls of the first factories was a quiet revolution, one forged in fire and necessity. The Industrial Revolution demanded a new kind of architecture, not for gods or kings, but for machines. These vast humming looms and spinning frames required space, light, and above all, protection from the catastrophic fires that could level a timber-framed building in hours. The answer emerged from the blast furnace, a material that seemed both a curse and a blessing: cast iron. It was strong under compression, far stronger than wood, and it would not burn. Yet in its early form it was brittle, prone to snapping if bent or shocked. The genius was in how the first industrial architects used it, not as a solution, but as the perfect partner for traditional masonry. They designed buildings like the Flax Mill, often called the world's first iron-framed building, with a brilliant composite logic. The external walls remained thick, load-bearing brick, providing stability and enclosure against the weather. But inside, the entire concept of support changed. Instead of a forest of wooden posts and beams, a neat, rational grid of slender cast iron columns rose through the floors. From these columns sprouted cast iron beams, spanning the open space to create wide, unobstructed floors. This was the birth of the clearspan interior. For the first time, the internal layout of a building was completely freed from the need for supporting walls. Managers could arrange and rearrange heavy machinery in any configuration, maximizing efficiency under the light from long factory windows. This iron skeleton, caged within its brick shell, was a composite system of profound implication. The brick handled the lateral stability and the weather, while the iron handled the precise, heavy loads from above. It was a division of labor written in architecture. But perhaps its most revolutionary feature was simply this: it did not catch fire. In an era defined by the risk of catastrophic loss, this composite design offered a form of economic security, allowing capital and industry to grow upward, story by story. This functional mill architecture, devoid of ornament, was quietly solving the central puzzle of modern building. It was achieving the complete separation of the structural frame from the building's skin. The walls were no longer holding up the floors, they were merely wrapping them. This idea, born in the pragmatic world of textile production, would become the defining principle of the next century, waiting only for a new material to take the next logical step. The factory's hidden iron skeleton was about to step into the light and become the star of the show. In 1851, London's park was transformed not by stone or brick, but by a shimmering mirage of iron and glass. The Crystal Palace, built to house the Great Exhibition, was more than a building, it was a manifesto. Joseph, a gardener accustomed to building vast greenhouses, saw the problem of erecting a monumental structure in mere months not as a limitation, but as a puzzle of assembly. His solution was a composite vision of breathtaking clarity and logic. He designed a rigid modular framework entirely of iron. Cast iron columns acted as the vertical supports, while stronger, more flexible wrought iron girders spanned the spaces between them, creating a perfect grid. This was a prefabricated kit of parts, every beam and bolt designed to be mass-produced in factories, shipped to the site, and assembled with astonishing speed, like a child's construction set on a gargantuan scale. But the true genius was in the infill. Into this rational iron grid, workers fixed enormous panes of the largest sheets of plate glass yet manufactured. This was the composite partnership made spectacularly visible. The iron did all the work of holding the building up, bearing the loads and resisting the wind. The glass did none of that work. It simply enclosed the space, creating a barrier against the weather while dissolving the very idea of a wall. Each material performed only the task it was best suited for, and the result was a style that felt utterly new. Walking through the Crystal Palace was an experience of sublime transparency. Sunlight flooded the interior, illuminating the exhibitions of industry from every nation without a single dark corner. The boundaries between inside and outside seemed to vanish, creating a volume of space that felt both immense and weightless. Critics called it a dematerialized architecture, a building that seemed to be more about the space it contained than the substance it was made from. This composite logic, this separation of structure and skin taken to its extreme, did not just house an exhibition, it became the exhibition's most powerful symbol. It pointed directly to the future. The grand train sheds of the great railway stations, with their soaring iron and glass roofs, are its direct descendants. But more importantly, the Crystal Palace planted the seed for the ultimate evolution of the composite idea, the modern curtain wall. It proved that a building's exterior could be a mere membrane, a lightweight skin of glass hung from a rigid internal skeleton, waiting only for the development of a new, even stronger structural material to make that vision soar to new heights. The shimmering promise of the Crystal Palace demanded a stronger backbone. That strength arrived in the fiery heart of steel mills, a material that would not just support glass but would lift entire cities into the sky. This was the final decisive leap in the composite story, the shift from iron to its vastly superior cousin steel. While cast iron was strong but brittle, and wrought iron was tough but relatively soft, steel combined the best of both. Through new industrial processes like the Bessemer converter, manufacturers could now produce steel in massive quantities, a material with unparalleled tensile strength and resilience. It could be rolled into standardized I-beams, perfect for framing, and it could be riveted into a rigid, continuous skeleton. This was the key that architects in one particular city were desperately searching for. Chicago in the 1880s was a city literally rising from the ashes, following a devastating fire that had leveled its largely wooden downtown. The urgent need to rebuild quickly, safely, and densely created a perfect laboratory for innovation. Here, architects like William Barron looked at the problem of height not as a question of piling stone upon stone, but of weaving a new kind of structural web. His home insurance building, completed in 1885, is often cited as the first true skyscraper, not because of its height, which was a modest 10 stories, but because of its hidden revolutionary core. Designed a complete skeleton of wrought iron and steel beams and columns. This metal framework, erected story by story, carried every ounce of the building's weight, from the floors to the walls to the roof. The exterior masonry was no longer a load-bearing wall, it was a curtain. This is the birth of the curtain wall, a term of profound significance. The brick and terracotta facade was literally hung from the steel frame, a lightweight, weatherproof skin that bore no structural burden. This was the ultimate expression of the composite principle, the complete and final divorce between a building's bones and its skin. The steel frame handled all the forces of gravity and wind, a task it performed with silent, immense efficiency. The wall, freed from its ancient duty, could now be anything. It could be thinner, it could be mostly window, it could be adorned or plain. This single breakthrough solved multiple problems at once. It allowed for unprecedented vertical growth, as adding another floor simply meant extending the steel grid upward, unshackled by the crushing weight of lower stone walls. It revolutionized construction speed, as prefabricated steel members could be riveted together with breathtaking pace compared to slow stone masonry. And it fundamentally changed the experience of the interior, flooding office floors with natural light through those large, continuous windows made possible by the slender metal mullions. The Chicago School architects, as they came to be known, embraced this logic to create a new aesthetic of verticality and clarity. Their buildings stepped back at higher levels to allow light to reach the streets. They celebrated their grid-like structure with large windows and minimal ornament, and they used materials like terracotta, a fired clay that could be molded into decorative panels, as a lightweight, fireproof cladding for their steel bones. This was not just a new way to build, it was the birth of the modern city's iconic silhouette, a style born from the pure, elegant partnership of a steel skeleton and a non-load-bearing skin. The skyscraper was not invented, it was discovered, the inevitable architectural form waiting for the right composite key to unlock it. But the steel skeleton, for all its strength, remained a rigid cage. It excelled at creating the straight lines and right angles of the modern grid, but it could not easily bend or flow. For architects dreaming of curves, of shells, of structures that felt grown rather than assembled, a different kind of composite was needed, one that was not a frame with a skin, but a single monolithic substance that could be both. That material emerged from a simple, brilliant fusion, the marriage of concrete and steel into one inseparable entity, reinforced concrete. The principle is deceptively elegant. Concrete, like stone, is immensely strong when compressed, when weight pushes down on it. But ask it to span a gap or resist bending, and it will fail in tension, cracking and pulling apart. Steel, however, thrives under tension. It is fantastic at resisting those pulling forces. The innovation was to embed steel rods, called rebar, directly into the wet concrete. As the concrete sets, it grips the steel with a fierce mechanical bond. More importantly, the two materials have almost identical rates of thermal expansion and contraction, meaning they move as one with changes in temperature, preventing internal stresses from tearing them apart. This union creates something entirely new, a synthetic stone with a hidden metallic nervous system, a material that can be poured into any imaginable shape and trusted to hold it. One man, a French engineer named, saw the monumental potential in this partnership. He patented a complete building system in the 1890s, designing not just the material, but the very method of using it, with detailed calculations for how to place the rebar to resist specific stresses. Did not just sell a product, he sold a vision of total architectural freedom. With reinforced concrete, the very language of form changed. It enabled the cantilever, that breathtaking act of architectural defiance where a structure extends horizontally into space with no visible support below. Frank writes is its most poetic expression, where concrete trays seem to float effortlessly over a waterfall, anchored only by their connection to the central core. The material made this gravity-defying feat structurally sound, its steel tendons locked inside the concrete, holding the dramatic overhangs in a permanent, invisible embrace. But the possibilities went far beyond the cantilever. In the hands of engineers like Italy's Pier, reinforced concrete became a medium for structural artistry. Designed vast, thin parabolic shells for aircraft hangars and sports palaces, forms derived from the natural efficiency of an eggshell. These were not decorations applied to a structure. The beautiful, ribbed pattern on the ceiling was the structure itself, a single, flowing surface of incredible strength and lightness. This monolithic quality led directly to the bold, sculptural masses of brutalist architecture in the 20th century, where the raw, board-marked surface of the concrete was left exposed as the final finish, celebrating the honesty of the material itself. Reinforced concrete became the ultimate plastic material for architectural expression, a clay that could harden into any form the mind could conceive. It was structure and skin fused into one, the final logical step in the composite journey, a material that could be at once monument, shelter, and sculpture. This composite triad became a manifesto, a set of principles as clean and sharp as the buildings it created. Modernism did not just use steel, glass, and concrete, it their inherent truth. Architects like Ludwig van and saw these materials not as mere substance, but as a philosophical toolkit, each component serving a pure and singular purpose in the service of a new way of living. The steel frame was the ultimate minimalist, a precise, rational grid that brought order to chaos. It provided the absolute minimum of structure, a skeleton of breathtaking elegance that declared everything else was optional. Into this grid, walls of glass were hung, dissolving the ancient barrier between interior and exterior in a way even the Crystal Palace could only hint at. Light and view became the primary materials, not brick or stone, and spanning between the steel members were the smooth planes of reinforced concrete, creating vast, unencumbered floor slabs. This technical composite was the direct physical enabler of the International Style's core commandments. The principle of volume over mass, where space itself was the important element, not solid walls, was made possible by that slender steel frame holding up a glass skin. The demand for regularity and repetition was a natural outcome of prefabricated steel and standardized glass panels. And the famous absence of ornament was a moral statement, a belief that beauty should come solely from the inherent qualities of the materials and the perfection of their proportions, not from applied decoration. The ultimate expression of this faith is Van's building in New York. It stands as a temple to the composite triad. Its structural frame is not hidden, but celebrated in a skin of bronze-toned steel I-beams, running vertically up the facade like a drawn curtain. Between these bronzed mullions are panels of tinted glass, creating a shimmering, austere grid that reflects the sky and the city. There is nothing extra, nothing applied. The entire sleek, corporate aesthetic of the mid-20th century, that language of power and cool rationality, flows directly from this one building's material honesty. It showed the world that the composite techniques born in factories and mills could be refined into high art, defining an era's ambition not with carved stone, but with the precise, luminous partnership of steel and light. Yet that sleek glass box represented only one direction for the composite mind. The same material that created the rigid grid could also be taught to dance. Engineers began to push reinforced concrete to its most elegant and extreme conclusion, asking a radical question. How thin could a structure become before it failed? The answer lay not in adding more material, but in discovering the perfect shape. This was the birth of the thin-shell structure, a revolution of breathtaking lightness. Visionaries like Spain's and Mexico's Candela looked beyond the beam and the column, finding inspiration in nature's own engineering, in the strength of an eggshell, the curve of a leaf, or the saddle shape of a hyperbolic paraboloid. Their genius was in understanding that with the right geometry, a shell only a few inches thick, reinforced with a fine mesh of steel, could span distances that once required forests of columns. The shape itself became the structure. A doubly curved surface, like the gentle saddle of a, distributes stresses so efficiently that every part of the shell works in unison, with compression and tension flowing along its natural lines like forces across a soap film. This was composite thinking distilled to its form. The steel and concrete fused into a single, continuous membrane that was both roof and wall, structure and skin. Candela, in particular, became a master of this technique, constructing vast, column-free market halls, churches, and factories across Mexico. His work feels almost miraculous, roofs that appear to float like concrete fabric draped over space. The Church of Our Lady of the Miraculous Medal in Mexico City is a stunning example. Its roof, a series of flowing, folded hyperbolic paraboloids that create a soaring, luminous interior from a shell just 1.5 inches thick. To stand beneath it is to witness the complete dematerialization of mass, where the heaviest of materials is made to feel weightless. This style was one of pure geometric expression, of dramatic, sweeping curves that cast ever-changing shadows, a direct architectural dialogue between mathematics and material. It demonstrated that the ultimate efficiency could also yield sublime beauty, proving that the most advanced material science does not have to feel cold or industrial, but can create spaces of awe and serenity. The thin shell was the final proof that in the right hands, a composite is not just a way to build, it is a way to think, to see the hidden potential for strength and grace in the very air we wish to enclose. That thin shell of concrete was a masterpiece of fusion, but the modern skyline demanded a different kind of magic, one of reflection and separation. The true legacy of the Chicago frame was not a heavier material, but a lighter skin, perfected into an art form known as the curtain wall. This was no simple wall, it was a high-tech sandwich, a layered composite system hung like a delicate garment from the building's sturdy steel shoulders. Its genius lies in its singular purpose, to manage everything the outside world throws at a building, while bearing absolutely none of its weight. A typical curtain wall is a marvel of coordination. Its bones are a slender grid of extruded aluminum, a metal chosen for its lightness, strength, and resistance to rust. This grid is the scaffold, precision engineered to hold the two key components. The first is the vision glass, large panels of insulating glass that fill the spaces where people need light and view. The second is the spandrel panel, often a solid sheet of metal, stone, or opaque glass, which covers the floor slabs, the mechanical spaces, and the structural edges, creating the building's characteristic banded appearance. Each layer has a dedicated job. The aluminum frame provides the structure for the wall itself. The glass provides transparency and thermal control. The spandrel provides privacy, insulation, and a finished look. And between them, all are hidden seals, gaskets, and drainage channels, a silent network designed to manage water, wind, and temperature shifts. This was composite thinking scaled to the size of a city block. By perfecting this prefabricated kit of parts, architects and developers could now clad a 50-story tower with astonishing speed. Entire facade sections could be assembled in a factory, shipped to the site, and simply bolted into place onto the waiting structural frame, floor by floor. This method revolutionized commercial construction, making the glass box skyscraper not just an aesthetic choice, but an economically irresistible one. It created the iconic mirrored skyline of the late 20th century, where buildings ceased to be opaque monuments and became vast, shimmering canvases that reflected the clouds, the sun, and each other. To walk through a financial district is to walk through a canyon of these composite skins, a landscape defined not by mass, but by light and illusion, the final, elegant divorce between what a building is and how it appears to the world. Yet even the most fluid concrete shell required time and skilled labor on site, a slow art in an age of accelerating demand. The solution emerged not from the architect's drawing, but from the logic of the factory floor itself. Precast concrete took the ancient alchemy of cement, aggregate, and steel and industrialized it, turning building components into mass-produced, modular units. The process was of efficiency. In a controlled factory environment, workers could pour concrete into precisely engineered steel molds, embedding complex networks of rebar, and even adding finishes, textures, or pigments directly into the mix. Each unit cured under ideal conditions, free from the unpredictability of weather, resulting in a product of exceptional strength and consistent quality. These elements, whether they were massive wall panels, long double T-beams, or intricate components, were then shipped to the construction site as finished pieces of a giant three-dimensional puzzle. On site, the process shifted from crafting to assembly. Cranes lifted these hefty modules into position, where they were bolted, welded, or grouted together onto a waiting structural frame. This was construction reimagined as a swift, precise operation, where the building seemed to rise from the ground in a matter of days rather than months. Each precast unit was, in itself, a perfect miniature of the composite principle, a dense, durable skin of concrete permanently married to its hidden steel skeleton. But this method did more than just speed things up. It fundamentally shaped a new architectural aesthetic. Because the molds could be reused to create identical units, precast construction naturally favored bold, repetitive geometries. It gave rise to a style of powerful sculptural massing, where the rhythm of identical modules created a striking visual pattern. The texture of the mold itself, often made of board-formed wood or ribbed rubber, became imprinted on the concrete surface, leaving behind a raw, tactile record of its industrial origins. Architects embraced this language wholeheartedly. In his brutalist buildings, such as the Yale Art and Architecture Building, he used precast concrete panels with deeply recessed joints and rough hammered finishes. The building's formidable layered appearance was not applied decoration. It was the direct, honest expression of how it was made. The very method of fabrication, the logic of the reusable mold and the crane's lift, became an integral part of the architectural statement. This technique enabled the rapid construction of monumental projects that defined the mid-century landscape, from the soaring, cantilevered tiers of sports stadiums to the vast, repetitive facades of university campuses and housing complexes. It proved that the drive for efficiency and scale could produce its own kind of rugged, rhythmic beauty, a style where the mark of the machine was not hidden, but celebrated as the signature of a new era. The rigid geometry of the box was a cage that could not hold every dream. For visions of vast, unobstructed space under a single roof, architects needed to think beyond the linear beam and column, to build in 3 dimensions from the very start. This was the birth of the space frame, a composite network that turned the entire building into a single, giant truss. Imagine a child's construction set, but instead of building a solid wall, you create a 3-dimensional lattice of identical metal struts, usually steel or aluminum, connected at precise points called nodes. This interconnected web is the key. Because it distributes forces in every direction, a space frame achieves incredible strength and rigidity with a stunning economy of material. It is not a skeleton supporting a separate skin. It is a composite entity where the structure and the enclosure become one and the same. The resulting style is one of crystalline logic, a high-tech transparency where the intricate pattern of the frame itself is the primary architectural expression, often left fully exposed. This principle found its most poetic and influential expression in the mind of an American visionary, Fuller. He looked at the problem of enclosing space and asked a radical question inspired by nature. What is the most efficient way to distribute stress across a curved surface? His answer was the geodesic dome. A geodesic dome is essentially a space frame bent into a spherical shape. It is built from a network of straight, lightweight, often aluminum or steel, arranged in a complex pattern of triangles to form a rigid self-supporting shell. The triangle geometry's most stable shape is the hue. This composite assembly creates a structure of breathtaking efficiency, capable of spanning enormous distances with almost no internal supports while using a fraction of the material a conventional dome would require. Fuller's own iconic domes, like the one built for the 1967 Montreal Expo, were marvels of lightweight engineering, appearing like delicate geometric bubbles yet strong enough to withstand tremendous loads. The style this technique enabled was unabashedly futuristic, celebrating the beauty of mathematical order and structural honesty. It influenced everything from the dramatic glass-roofed atriums of modern airports and shopping malls to the vast, column-free spans of sports arenas and exhibition halls. Walking beneath a geodesic dome, you are enveloped not by solid mass, but by a luminous lattice, a perfect marriage of mathematical idea and material reality that makes the immense feel light, and the complex feel elegantly simple. The geodesic dome revealed a hidden truth, that the most advanced structures could wear their logic on the outside. But what if you took that idea and ran with it, turning every pipe, every bolt, every steel beam into a vibrant public spectacle? In the 1970s and 80s, a group of architects did exactly that, launching the high-tech movement. Led by visionaries like Norman Foster and Richard Rogers, they pushed composite construction to its most expressive and radical conclusion. Their philosophy was one of radical honesty. Instead of hiding the complex systems that make a modern building function, they would celebrate them. They would take the entire kit of parts, the steel skeleton, the air conditioning ducts, the water pipes, the electrical conduits, and even the elevators, and pull them to the outside of the building. The result was an architecture that looked less like a static monument and more like a living, breathing machine. The most famous example is the Center in Paris, designed by Rogers and Piano. To a Parisian used to stone facades and classical proportions, it must have looked like an alien refinery had landed in the historic district. The building's entire structural and mechanical system is displayed on its exterior in a riot of color-coded components. Giant diagonal steel braces form the exoskeleton, painted a bright white. Snaking across this frame are ducts and pipes in vibrant blues for air, greens for water, and yellows for electrical systems. The escalators, those tubes of moving people, are encased in clear plastic snaking up the main facade. This was not just a building, it was a diagram in 3 dimensions, a declaration that the true beauty of the modern age lay in its functional clarity. Every piece had a purpose, and every purpose was made gloriously visible. The style transformed the building from an opaque object into a transparent lesson in how things work. Inside, this externalization of services created vast, flexible, column-free floors, perfect for the museum's ever-changing exhibitions. The composite was no longer a hidden partnership, it was the star of the show. A similar logic drives the Lloyd's of London building, designed by Richard Rogers years later. Here, the exoskeleton is even more pronounced, a cluster of stainless steel towers, ducts, and glass capsules clinging to the sides of a central atrium. It resembles a futuristic cityscape in miniature, with its services stacked neatly in external towers to keep the core open and adaptable. The aesthetic is one of precise engineering and dynamic assembly, as if the building could be taken apart and reconfigured for a new purpose tomorrow. This high-tech style celebrated the composite nature of modern construction by making the technical assembly the entire architectural statement. It blurred the line between building and machine, suggesting that our greatest structures could be as logical, as serviceable, and as honestly beautiful as a well-made watch. It asked us to find elegance not in applied ornament, but in the intelligent organization of parts, a final, bold confession of how our world is truly made. The machine aesthetic celebrated a building's inner workings, but it still faced the oldest and most relentless of foes, the weather itself. Truly modern building needed a smarter skin, one that could think for itself. This led to the evolution of the simple wall into a highly engineered, multi-layered composite system, a technological envelope for the entire structure. The most sophisticated of these is known as cladding, a concept that fundamentally rethinks how a building interacts with the elements. It is no longer a single, solid barrier, but a dynamic, layered assembly, each stratum with a dedicated and intelligent purpose. The outermost layer is the cladding itself, a durable skin of metal panels, terracotta, fiber cement, or even high-pressure laminate. This is the first line of defense, taking the brunt of rain, sun, and wind. But here is the crucial innovation: it is not sealed tightly against the next layer. Instead, it is mounted with a small but vital gap behind it, a continuous air cavity. This cavity is the system's secret weapon. When wind-driven rain penetrates the tiny joints in the outer cladding, it hits the back of that panel and is channeled downward by gravity, draining out through weep holes at the bottom. Simultaneously, the cavity allows air to circulate, carrying away any residual moisture and equalizing air pressure, which prevents water from being forced deeper into the wall. Behind this ventilated cavity lies a continuous blanket of high-performance thermal insulation, keeping interior temperatures stable. And finally, sealed directly to the building's structural frame is an inner air and water barrier, an airtight membrane that acts as the final defensive line. This composite assembly is an immaterial partnership. It manages moisture, heat, and air movement in a coordinated way that a single, massive wall of brick or stone simply never could. A traditional masonry wall tries to be a monolithic shield, often trapping moisture inside where it can cause decay. The, however, is a breathable, layered system that manages water intelligently, acknowledging that some will get in and providing a clear path for it to get back out. This technical leap has liberated architectural expression in profound ways. Because the outer cladding is non-structural and protected by the cavity behind it, it can be almost anything. It allows for the bold, vibrantly colored facades of contemporary museums and cultural centers, where large, durable panels can be arranged in dramatic patterns. It enables the use of delicate-looking terracotta that give a building a warm, textured appearance while being incredibly resilient. The style of a building becomes as much about its environmental performance as its visual impact. Sleek, colorful, and often intricately patterned skyscrapers and civic buildings that define our skylines are direct products of this composite thinking. Their beauty is not just skin-deep, it is the visible result of a deep, layered intelligence, a silent conversation between materials engineered to outsmart the storm. But that layered, intelligent skin is only the beginning. We are now entering an era where the very idea of a building component is being rewritten, not by hand, but by code. Composite story is merging with the digital revolution, creating a new frontier where form and information are fused into one. Today's most advanced structures begin not on a drafting table, but inside a computer model, a virtual space where architects can design shapes of breathtaking complexity, forms that nature herself might recognize, all governed by the precise logic of mathematics and physics. These are not shapes you can easily build with standard steel beams or poured concrete. They demand a new kind of material partnership, one born from this digital womb. Enter materials like carbon fiber reinforced polymers. Think of them as the high-tech descendant of mud and straw. Extremely thin, incredibly strong strands of carbon are woven into a fabric, then set within a plastic resin. The result is a composite material that is astonishingly light, yet possesses a strength-to-weight ratio greater than steel. But its true magic is its malleability during fabrication. This fabric can be laid up in molds of virtually any shape, then cured to create a rigid, seamless component of extraordinary lightness and strength. This is the key that unlocks the digital design. That undulating, flowing roof of center in Baku, with its seamless curves that seem to rise from the ground like a frozen wave, would be impossible with traditional materials. It was made possible by a composite skin precisely engineered to follow the digital blueprint, where every panel's unique curvature was calculated and fabricated to fit its exact place in the whole. The composite here is no longer just a combination of substances, it is the physical manifestation of digital data. The architectural style this enables is one of unprecedented fluidity and organic complexity, where walls melt into ceilings and structure flows into space in a continuous, sweeping gesture. It is a computationally driven language, where the building becomes a three-dimensional printout of an algorithm, a frozen moment of dynamic motion. This digital composite synergy suggests that the future of monumental architecture may not lie in assembling standardized parts, but in growing unique, optimized forms, where every gram of material is placed exactly where the digital model says it is needed for strength and beauty. The blueprint and the building are finally becoming the same thing. That digital wave of concrete and carbon fiber has brought us to the present moment, but the most important question is no longer just what we can build, but how we can build without costing the earth. The climate crisis demands a fundamental reinvention of our materials, and the composite principle is rising to meet it, this time with a focus on regeneration. The most promising answer is emerging not from the lab, but from the forest in the form of engineered mass timber. At the forefront is cross-laminated timber, or CLT, a material that is a brilliant composite in its own right. Picture this: layers of standard dimensional lumber, like 2x6 boards, are stacked atop one another. But here is the key: each successive layer is oriented at a 90-degree angle to the one below it. These layers are then glued together under immense pressure to form solid monolithic panels that can be the size of an entire wall or floor slab. This cross-lamination is the genius. It mimics the grain structure of plywood but on a massive scale, giving the panel exceptional dimensional stability and strength in all directions. It turns ordinary wood, a material prone to warping and with variable strength, into a predictable high-performance building component. This engineered wood composite is sparking a quiet revolution, enabling the construction of tall wooden buildings, structures that reach 8, 10, even 18 stories high. The architectural style this fosters is profoundly human, a warm aesthetic that connects us directly to nature. Stepping inside a building like the Tower in Norway, the world's tallest timber building when completed, is an experience of calm and warmth. The exposed wood ceilings, columns, and beams create an interior that feels organic and inviting, a stark contrast to the coolness of steel and concrete. But the appeal is far more than skin deep. Wood is a renewable resource that sequesters carbon, meaning it stores the carbon dioxide the tree absorbed during its growth, locking it away for the life of the building. This makes mass timber construction a powerful tool for reducing a building's embodied carbon footprint from the very start. The composite thinking, however, does not stop at the structure. The next layer integrates green technology directly into the building's skin, creating a living, responsive envelope. Architects and engineers are now designing composite facade systems that do double or even triple duty. Building-integrated photovoltaics are no longer clumsy add-ons. They are sleek, crystalline tiles or spandrel panels that replace conventional cladding, turning the entire south-facing wall or roof into a silent power generator. Other systems embed phase-change materials within walls or ceilings. These are special substances that melt and solidify at room temperature, absorbing excess heat during the day and releasing it at night, acting like a thermal battery that smooths out indoor temperature swings and drastically cuts energy use. We are moving toward a style where sustainability is not an added feature or a badge of honor. It is the intrinsic logic of the form itself. The building's shape might be optimized for passive solar gain. Its skin might harvest rainwater and filter it for reuse, and its very bones might be grown from sustainably managed forests. This points toward a carbon-neutral architectural future, where every material partnership, from the massive CLT panel to the thin film photovoltaic layer, is chosen for a singular, unified purpose: to create shelter that gives back more than it takes. The story of composite construction, which began with straw holding mud together, is now culminating with buildings designed to hold the future together. The Pantheon's dome has watched empires rise and fall, yet its concrete shows no sign of stopping. This longevity is not a mystery of magic, but of a lost recipe, a secret locked within the very chemistry of the ancient Roman world. For centuries, the formula for this self-healing concrete was a forgotten chapter, a technological high point that vanished with the empire itself. Modern concrete, by stark contrast, is designed for speed and immense compressive strength, but it lacks the innate flexibility and durability of its ancient ancestor. In harsh environments, especially in contact with seawater, modern structures can begin to degrade in mere decades, their steel reinforcement corroding and causing the concrete to crack and spall. The Roman version, however, seems to grow stronger with time, particularly in marine environments. The key was not just what they used, but how those ingredients worked together as a perfect composite. The magic ingredient was a specific volcanic ash, pozzolana, mined from regions like. When Roman engineers mixed this fine, reactive powder with lime and seawater, they initiated a slow, hot chemical conversation that modern science is only now beginning to fully translate. Using tools like microspectroscopy to peer into the material's atomic structure, researchers have found something astonishing. As seawater percolated through the concrete over centuries, it dissolved components of the volcanic ash and lime, allowing them to recrystallize into rare plate-like minerals that filled any developing microcracks. This was a living material, one that could repair itself. The composite was not a static mixture, it was a dynamic system, designed to evolve and strengthen in response to the very elements that threatened to destroy it. This ancient smart material poses a profound question for our future. In our rush for rapid construction, have we overlooked deeper, more resilient forms of material wisdom? The Roman recipe reminds us that the most advanced solutions are not always the ones. Today, teams of archaeologists and materials scientists are racing to reverse engineer this 2,000-year-old technology, not to copy it, but to understand its principles. Could we design modern, low-carbon concretes that incorporate similar self-healing properties, perhaps using different local reactive materials? The puzzle of Roman concrete is more than a historical curiosity, it is a direct challenge from the past, suggesting that the secrets to building a lasting, sustainable future might be waiting for us in the silent chemistry of ancient ruins. A building is more than a shelter, it is a statement of belief, a poem written in stone and light. The silent dialogue of composite materials did not just solve engineering problems, it gave voice to entire civilizations, allowing them to articulate their deepest spiritual and cultural identities in forms that would have been otherwise impossible. Nowhere is this more evident than in the shimmering, golden heavens of Byzantine churches. The challenge for Byzantine architects was profound, to create a space that embodied the celestial hierarchy of Orthodox Christianity, a centralized, domed interior that focused all attention upward toward the divine. Their solution was a masterful composite of humble materials, brick and mortar. Instead of carving massive stone blocks, they constructed their iconic domes and semidomes from layers of thin, lightweight bricks, each course set in a thick bed of mortar. This technique, essentially a bricklayer's art raised to a cosmic scale, allowed for incredible flexibility. They could build complex curving geometries that stone masonry would resist, creating a cascading series of vaults that seemed to float weightlessly. The composite nature of the system was its genius. The mortar allowed for slight adjustments as the dome rose, accommodating the precise geometry needed to transfer the immense weight down to the supporting piers and walls below. This engineering triumph enabled the central plan church, a design where the congregation gathers under a central dome representing the vault of heaven. Inside that dome appears to hover on a ring of light from 40 windows, an effect made possible by the delicate brickwork composite that minimized the visual bulk of the supports. The mosaics that later covered these surfaces, glittering with gold leaf and colored glass, were the final layer of this spiritual composite, transforming the engineered shell into a vision of the eternal. The architectural identity of Byzantium, its mystical, luminous interiority, was born directly from the mastery of brick and mortar. A world away, under the bright sun of the Indian subcontinent, a different empire expressed its power and refinement through another exquisite composite dialogue, this one in stone. Architecture, culminating in the Taj Mahal, represents a sublime fusion of cultures and materials. The builders employed a composite technique both structural and decorative. The primary structure used robust, locally sourced red sandstone for its strength and availability, forming the massive walls, gates, and minarets. But the soul of the building is its skin, a veneer of luminous white marble from distant quarries. This marble cladding, a non-structural composite layer, was then transformed by the art of Dura. Craftsmen would intricately inlay the marble with precious and semi-precious stones, like lapis lazuli, carnelian, and jasper, creating flowing floral patterns and calligraphic verses from the. This was a composite of color and light, where the hard, permanent stones were pieced together like a delicate, eternal mosaic. The visual effect is one of breathtaking harmony and opulence, the warm, earthy red sandstone framing the cool, ethereal white marble tomb, which itself blossoms with intricate jewel-like detail. This material partnership was not accidental, it was a deliberate artistic language. The fusion of strong local stone with precious imported marble mirrored the empire's own synthesis of Persian, Islamic, and Indian influences. The Taj Mahal is not just a building, it is a perfect sentence written in a composite language of geology and culture, where every material choice speaks of permanence, paradise, and love. From the golden domes of Byzantium to the marble inlay of the Taj Mahal, a powerful truth emerges. The development of a unique architectural style is never purely an artistic whim. It is a conversation with the materials at hand and the knowledge of how to combine them. The Byzantine central plan could not exist without the flexible brick composite. The iconic dura elegance of the could not exist without the strategic layering of sandstone and marble. In each case, the available technology, the mastery of composite techniques, became the very alphabet with which a culture wrote its identity into the landscape. This reveals that construction is not a separate discipline from art or spirituality, it is their foundation. The way a society builds, the partnerships it forges between earth and fire, stone and mortar, directly shapes the spaces where it worships, governs, and dreams. The quest for architectural identity begins not on the drawing board, but in the understanding of how different elements can be brought together to create something entirely new, something that speaks in a voice unmistakably its own. A solid block of marble is a masterpiece of nature, but it is also a prison for the architect's imagination. For thousands of years, builders were confined by the inherent, unchangeable properties of pure materials. To understand the breathtaking leap of composite construction, we must first stand before these ancient walls and recognize what they could never be. Stone, in its monolithic glory, possesses immense compressive strength. You can stack it high, as the builders of the pyramids did, creating mountains of geometric precision that defy time. Yet that very strength reveals a critical weakness. Try to span a space with it, to create a room beneath a stone roof, and the material betrays you. A stone lintel or a simple barrel vault pushes outward with tremendous lateral thrust. To contain that force, the walls supporting it must be absurdly thick and heavy, leaving little room for light or openness. The interior of a great pyramid is not a grand hall, it is a series of narrow, claustrophobic passages. The material's own logic demanded solid mass over spacious volume. Timber offered a different path. It could be shaped and joined to create wide roofs and flexible frames, bringing warmth and a human scale to structures. But its purity was its peril. A world built of wood is a world living in the shadow of flame and rot. The great conflagrations that swept through medieval cities were a constant, terrifying reminder of this vulnerability. Furthermore, wood's organic nature means it bends, warps, and weakens over time under constant load. A pure timber tower of any significant height would sway uncontrollably in the wind, its very flexibility becoming a fatal flaw. And then there is glass, the most seductive and deceptive of pure materials. It offers transparency, a perfect marriage of enclosure and vision. Yet by itself, glass is a fragile skin with no structural bone. A building made only of glass panes would be a sculpture of imminent collapse, unable to bear its own weight or resist the slightest pressure. Each of these magnificent substances, alone, represented a dead end. The stone building was dark and confined. The timber building was ephemeral and vulnerable. The glass building was an impossible dream. This was the great architectural stalemate. Progress was not a matter of wanting taller towers or brighter interiors. It was a physical impossibility dictated by the limits of monolithic thinking. The breakthrough did not come from finding a new perfect material, but from a radical shift in strategy. It was the moment builders stopped asking one substance to do everything and began to think like conductors, assigning specific specialized roles in a material orchestra. Let the stone do what it does best, bear immense weight in compression. Let the iron do what it does best, resist the pulling forces of tension. Let the glass do what it does best, admit light without bearing load. This strategic division of labor is the quiet, revolutionary core of the entire composite idea. It is what allowed architecture to transform from a craft of stacking and carving into a science of strategic partnership. That simple mental shift broke the stalemate. It dissolved solid mass into articulated skeletons of incredible efficiency. It pierced dark enclosures with walls of luminous glass. And it provided the hidden framework that would ultimately allow those impossible glass towers to not only stand, but to define our modern skyline. The history of building is, in many ways, the history of learning to see weakness not as a flaw to be hidden, but as an invitation for another material to lend its strength. The future of building is not about assembling inert parts, but about collaborating with life itself. We are entering an era where the composite principle will merge with biology, giving rise to materials that are not just smart, but literally alive. The next chapter moves beyond steel and concrete to explore living composites, substances that grow, heal, and respond to their environment. This is the frontier of biofabrication, where the very bricks and beams of our structures could be cultivated rather than cast. Imagine a concrete that does not just sit there, but actively maintains itself. Researchers are already developing concrete infused with dormant, specially selected bacteria. When a tiny crack forms and water seeps in, these microscopic organisms awaken. They feed on nutrients embedded in the mix and begin to secrete calcite, a natural mineral that is the primary component of limestone. This biological process slowly fills the crack from the inside out, effectively healing the wound before it can spread and threaten the structure's integrity. This is not science fiction. It is a practical application of a self-healing composite, a material system where a living component performs a vital maintenance role that would otherwise require costly human intervention. The building becomes, in a very real sense, an organism with an immune system. But why stop at healing? What if the building material itself could be grown from scratch with minimal energy and even absorb carbon from the atmosphere? This is the promise of mycelium composites. Mycelium is the dense, root-like network of a fungus, the unseen part of a mushroom. By taking this fast-growing biological matrix and combining it with agricultural waste like straw or wood chips, scientists can create a living slurry. This mixture is placed into molds of any desired shape, from packaging to architectural panels. Over a matter of days, the mycelium threads through the waste, binding it all together into a solid, lightweight block. The block is then heated to stop the growth, resulting in a strong, fire-resistant, and completely biodegradable building material. This process requires no high-temperature kilns, no carbon-intensive chemical reactions, just the quiet, efficient work of nature. The architectural style such materials could inspire is fundamentally different from anything we know. It would be dynamic and adaptive. A facade grown from mycelium composites could have a soft, textured, almost fuzzy appearance, feeling warm and organic to the touch. Structures might not have sharp, rigid corners, but flowing, curvilinear forms that echo growth patterns found in nature. More profoundly, these buildings would have a life cycle. At the end of their use, instead of being demolished into landfill, they could be composted, returning their nutrients to the earth to grow new materials, creating a truly circular system. This points toward a future where the boundary between the built environment and the natural world becomes beautifully blurred. We could see buildings that change color with the seasons because their cladding incorporates living algae, or walls that breathe and regulate humidity through their porous biological structure. The very concept of construction would shift from an extractive, assembly line process to a more gentle act of cultivation and partnership. It suggests a future where our shelters are not just built, but thoughtfully grown, woven into the ecological web as active participants rather than silent monuments. This is the ultimate evolution of the composite idea, a partnership not just between materials, but between human ingenuity and the intelligence of life. Perhaps the most profound composite of all exists not in a laboratory, but within the human imagination. Throughout this journey, we have traced the physical partnerships of straw and mud, iron and timber, steel and glass. Yet the architectural styles these techniques enabled are themselves a deeper kind of composite, a philosophical fusion of memory and ambition. No great style is ever born from nothing. It is always a conversation across time. Gothic architecture, for instance, is not a sudden rupture. It is a breathtaking composite of the solid, earthbound mass of the Romanesque and a new, vertiginous structural daring. It took the ancient form of the basilica and stretched it toward heaven, using the pointed arch and flying buttress to transform ponderous weight into skeletal lightness. The style is a dialogue between what was and what could be. Centuries later, the Renaissance performed a similar act of synthesis. Its style was a conscious composite of recovered classical ideals, the harmonious proportions of ancient Greece and Rome, fused with the practical engineering and new materials of its own era. The result was not a slavish copy, but a reinvention, using brick core construction and linear perspective to create a new humanist vision of order and beauty. Even modernism, which seemed to reject the past so vehemently, was itself a composite. It fused the raw, industrial materials of the machine age with a radical new social vision of light, air, and equality. The glass curtain wall was not just a technical feat, it was a moral statement about transparency and openness in society. Each of these epoch-defining styles emerged from a fertile middle ground, a creative tension between reverence for tradition and the thrilling pull of innovation. This reveals that the ultimate composite technique has never been about mortar or rebar alone. It is the synthesizing power of the human mind itself. We are the composite engines. We look back to understand the logic of the dome, the strength of the arch, the meaning of a sacred space. Then we look forward, armed with new materials and new dreams, and we begin to blend. We take the memory of stone and pair it with the possibility of steel. We inherit the form of the temple and reimagine it in carbon fiber. This process of intellectual synthesis, of blending inherited wisdom with revolutionary tools, is the endless wellspring of architectural evolution. It is why our built environment is never finished, always becoming. The story of composite construction, therefore, is more than a history of engineering. It is a mirror held up to our own restless creativity. Shows us that to build for the future, we must first be fluent in the languages of the past, listening carefully to the lessons whispered by every brick, every beam, and every vault that has come before. Our greatest structures will always stand at this crossroads, monuments to a mind that remembers, dares, and forever recombines. From the straw-reinforced bricks of ancient cities to the carbon fiber curves of tomorrow's museums, the story of architecture is the story of composite construction. We have traced a journey where each fusion of materials, concrete and ash, stone and iron, steel and glass, acted as a master key. These partnerships did not merely make building easier, they unlocked entirely new architectural languages, reshaping our physical and spiritual horizons. The soaring nave of a Gothic cathedral, the luminous grid of a skyscraper, the undulating roof of a modern museum, none of these would exist without that fundamental shift in thinking. It was the move from asking one material to do everything, to orchestrating a chorus where each substance sings its own specialized part. This technical evolution is the silent, indispensable partner to every stylistic revolution, the unsung hero behind the spaces that fill us with awe. When we look at our skylines today, we are not just seeing buildings of glass and steel. We are reading a physical library, seeing centuries of material innovation and human ingenuity made manifest in concrete, timber, and light. Each structure is a chapter in this ongoing dialogue between what is possible and what is dreamed. So what comes next? What new material conversation will define the next architectural age? Will it be the silent self-healing of bioconcrete, the warm, cultivated logic of massed timber, or a partnership we have yet to imagine? The story is far from over, and the next key is waiting to be forged. Share your visions for the future of building in the comments below, and if you enjoyed this journey through the hidden bones of history, subscribe for more explorations into the mysteries of the world we have